Hi folks, in this video we continue our formal proofs with quantifiers. You've already learned universal, elim, and existential intro. Those are the two easy rules with quantifiers. They're easy because you can apply those rules directly to something you want without having to do a subproof. If you know, for example, that every object has property P, you can just prove that A has property P or B has property P. That's an easy rule to apply, because a universal claim is incredibly strong. If you know every object in the domain has a certain property, that is a lot of information. But it's quite different if you're trying to prove every object in the domain has a certain property, like property P. So universal intro is one of those annoying rules because you're actually trying to prove something incredibly strong or powerful, something about all objects in the domain. Now, if you just had a finite number of objects in the domain, this might not seem so mysterious. For example, what if you only had 3 objects in your domain and I wanted to prove they all had property P? Then I could just prove that A has P and B has P and C has P, and I'd be done. I could just prove it about those 3 objects. It's clear that that would just take a finite amount of time. But the trouble is, first order logic is incredibly general. It can cover things that have infinite domains. First order logic is the fundamental logic of mathematics, with the natural numbers, for example, being an infinite number of numbers. They're unlimited. So if I wanted to prove that all natural numbers have a certain property, or all even numbers have a certain property, then I can't just go through the objects one at a time because there's an infinite number of them. My formal proof would never end. So you might be thinking, how could I ever do something like universal intro? This seems incredibly powerful. How could an inference rule like this work? Well, it is doable. It's possible. This is the fundamental basis of modern mathematics. It wouldn't be possible if we couldn't do a kind of proof like this. And the device that we need in order to do it is something you haven't seen before. So that's what makes these last 2 formal proof rules more difficult, but also incredibly useful. They're going to require subproofs. So in that sense, they're like the annoying rules of Boole, like reductio or proof by cases. But this is something that you can master and you can understand. The new thing that we need besides a subproof is this at n notation. What that does is it talks about an arbitrary object in the domain without specifying something particular about it. So think about the A in this at symbol for arbitrary and the n for a name. What I'm doing is I'm assuming that n is an arbitrary name. That's kind of what this notation symbolizes. And n then picks out an object in my domain without knowing anything about n in particular. And so in order for it to be totally arbitrary, n cannot appear outside this subproof. So there's a restriction on using arbitrary names that n is not allowed to appear anywhere outside of this subproof. So you can tell if you had to do two universal intro proofs in the exact same formal proof, because you had 2 quantifiers in the sentence, then you would need multiple arbitrary names. And we're going to use n as the first one. If we need another one, we'll use m. If you need a third one, we'll use l. So we're actually going to have 5 different arbitrary names in our language, l through n. And you appeal to one of those if you need to prove a universal sort of sentence. So the only formula I put in the assumption line is this at n notation. And then in order to make a universal proof work about property P, for example, if I want to prove all objects have P, then I just need to prove that my arbitrary object has P, because I didn't assume anything special about it. So if it holds of n, then it must hold of everything in the domain. And that's the basis for making this universal inference about all objects in the domain. Now, all you do is use a subproof to introduce this rule. So you just cite the subproof 3-6 or whatever those numbers happen to be in whatever particular case you're looking at. Okay, now the structure of this doesn't just work for simple sentences like P of X. If I want to prove something more complex inside the scope of this quantifier, like let's say that this is some more complex formula, all I have to do is reproduce that complex formula here. Because when you do this rule, you simply take what is inside the scope of the quantifier, like P of X, and have that be the final line of your subproof with n's instead of x's. And then whatever the structure of that line is, that's what becomes the structure of the formula inside the scope of your quantifier. Like here's another example. Let's say that I asked you to prove a sentence like this, P of X arrow R of XA. Notice the thing inside the scope of the quantifier is complex now, but that is no problem. Our rule can handle it. All you need to do is start with some arbitrary name. Always start with n as the first one if you haven't used it already in your proof. And you need to, that's an assumption line. You're making a new subproof, so it has to be justified with assume. And then the last line of that subproof is simply going to be whatever you want inside the scope of your quantifier, and instead having n's in place of x's. So always, whenever you start a universal intro proof, always sketch out this final line of the subproof, because that's what your goal is. That's how you know where you're headed. Otherwise, you wouldn't know how to structure that subproof if you don't know where it's going. And if you can do that, if you can get from an arbitrary name n to this particular formula here, then that's what allows you to stick a universal quantifier wide scope in front and then replace all of the n's with that variable that the quantifier binds. Again, you can choose whatever variable you want. They just have to be the same. If this were a y, then all of these x's would be y's, and that would be fine. And as long as y does not appear in this formula, then that would be valid. Of course, if y already appeared in here, like you have multiple quantifiers in the same sentence, then you would have overlapping scopes, and that would be a syntax error, so you couldn't do that. Okay, that's all theoretical. Let's practice it. So pause your videos now and see if you can figure out how to do this, and then I will walk through the solution with you. So pause your videos, please. Okay, let's talk about the answer. So this is a validity. Convince yourself that this sentence has to be true. Imagine this were like being the predicate dog and Q is being a cat. This just says all dogs are either dogs or cats. That has to be true. That's a logical truth. That's in fact a first order validity. We should be able to prove this in FOL from no premises. So how could we do so? The first thing you need to do, notice the structure. The main connective of your conclusion is this universal quantifier. So you should always sketch out a universal intro proof. This is just like AIntro. Anytime you have a universal conclusion, that's actually a really helpful thing in proofs, because this is always the best way to structure it and to proceed, which is first declare an arbitrary name. Since I haven't already used n in my proof, I'm going to use it. So I write at n in my formula line and write assume. Now, the next thing, remember I said, sketch out where you're going, because this doesn't have a main connective. This doesn't tell you how to keep going. There's nothing in this assumption line that tells you what to do next. You can't apply an elim rule to that, because all you know is that n is just a random object in the domain. You don't know anything about it. So we have to sketch out this line about where we're going in order to make progress. So this is what it looks like. Remember, you just put n in the place of these x's, and that's what I'm trying to get to. Now, that's my goal, and that is an arrow sentence. So here's where all of your knowledge of bool and prop from the first half of this course comes into play. It's the main connective of this, namely the arrow that tells me what to do. I love proving arrows. You just assume the antecedent and try to get to the consequent. And how do we do that? Well, you just look at the main connective here. This is an or. Luckily, if I know P of n, I know P of n or whatever else I want. That's just a disjunction intro on line 2. Now that I've proven those things, I just can justify this with AIntro. And now we're finally done. You can see the rule that we've been working on. Once I can prove this sentence, that's the end of the subproof, I'm done. I get to put a universal quantifier in front of it and substitute all of the n's for whatever variable I'm binding, namely x. And I just cite that one subproof. So you can see why I can prove this about object n, that if it's p, then it's p or q, because that has to be true. That has to hold as a matter of logic. And so that, since n was completely arbitrary, that has to hold for all objects in my domain. So there's your first example about how to use the universal intro proof. Okay, thanks.